Hi everyone, thank you for being here one more time. Um, there was 2 very busy weeks. Those last past weeks. I received my grades from my first round of tests of my college. So it was a very busy but interesting week. But now I have here a problem that I want to solve with two different approaches. In our lectures, we saw something interesting about this problem with different approaches. We solved this using Newtonian mechanics, and we use a second approach using more advanced mechanics, more exactly the Euler-Lagrange equation for um, Lagrangian mechanics, as how it's most commonly said. Okay, so we will be solving this problem of a simple pendulum. We have here, first we will be using Newtonian mechanics to solve this problem. We have here a mass m and a rope with a length L, and also we'll be considering that our system is ideal, that is that we do not have any friction or any other type of inconveniences with this system. Okay, so as mentioned, we will be start with Newtonian mechanics, and I already have here the diagram of the forces. Okay, so this is basically it. We have like a tension T exerted by the rope against the mass. Um, Also, we have the force exerted by the gravity here. The mass. Also, we'll be considering the system that the rope is doing an angle between the vertical line or the imaginary vertical line of the system, or the position or the rest position of the system. Here it's an angle theta, the same right here. So this is our setup for the system. If you see, the movement will be alongside that direction. Obviously, when the mass or the system is moving, this direction will be tangential. So the only thing here that exerts the acceleration, or the only thing that is doing the movement here in the system, is this force. This is the only thing that causes that our system is in movement. Okay, so based on our diagram, since we have here like diagram as this setup, will be considered that this part as the x direction of how we set up our coordinates. So we have here that using the Newton equations for the forces, we have that the sum of the forces will be the mass times the acceleration in the x part. Okay, so this is our first thing that we'll mainly consider. I will a little bit better. Okay, so this is our first thing right here to consider. Okay, but it will be a little bit difficult to use Cartesian coordinates to solve this problem. So we will be using polar coordinates. So we will be transforming polar coordinates. First of all, I just want to make a remark that based on basic stuff, we know that the velocity is the first derivative of the position, or using other notation, it will be x dot. And the acceleration of the system will be the second derivative of the system, of x, of the system, sorry, of the position, and it's notated with x double dot. So we'll be rewriting this thing and x double dot, okay, because this is the only force that makes the pendulum moves, the x force based on our diagram. Okay, so with that setup, we will need to transform our Cartesian coordinates in polar coordinates. It will be easier our approach on this method. Okay, so first we need to consider that since this is like our zero, okay, so our radius, because this is based on the movement, it's like making a circle, so we'll be considered that the radius of our circle will be constant and have a radius of L length, that is the length of the rope. Okay, so the other thing that we need to consider right here is the x position. Here the x position will be based on r theta. Okay, so this is basically not the x position, this is basically the equation of this arc right here, the equation of an circular arc. Okay, the length of this arc will be uh, provided by this equation. Okay, so using the substitution that we mentioned, x will be L theta. So the velocity of the system will be x dot. L is constant, so it remains as constant, and the angular velocity will be changing alongside this, so this is the only thing that changes. And our acceleration will be also L remains constant, and here we have our angular acceleration. So I will be using that substitution, and since this is the only force that is made on the system, so I will be adding this thing. So since our movement, this force will be against our movement, so I will be writing the force like that, mg sine theta. Okay, will be m, and our substitution right here, I'll double theta. Okay, so since the mass is not zero, we can like eliminate from the equation something like that, and rearranging some terms, we have L double dot plus G sine theta will be equal to 0, and leaving alone this term will be theta double dot plus G over L sine theta will be equal to 0. And this exact equation is most popularly used. In physics we usually use like an approximation to make this easier, because this exact differential equation cannot be solved by analytic regular methods. We use an approximation, but this is a very common equation in physics that is called the harmonic oscillator equation. So yeah, when we go with this approach, we found this thing, that this is the equation that governs not only the pendulum but other systems that oscillates. So this is our first approach of this problem that leads us to the harmonic oscillator. So I will be doing a second approach right here. I will be copying this, the majority of those things. Okay, and I will be using now the Lagrangian equations to solve the same system. Okay, so I will be removing this part. Okay, so Lagrangian methods involves this equation. We have the velocity, the derivative with respect of time with the partial of the Lagrangian with respect of the velocity, okay, minus the partial derivative of the Lagrangian with respect of the position. Generally, it is equal to the non-conservative forces of the system that is denoted in some books like this. But since we are considering that here our system is do not have any friction, or it only works with conservative forces, we will be doing this equal to 0. So this will be our approach to this part. So, and the other thing that it's important to remark, the Lagrangian, we'll denote with an L, is basically the kinetic energy of the system minus the potential energy of the system. The kinetic energy will be denoted with a T. Okay, so yeah, this will be our approach. And yeah, first we need to know the value of T. Since the only kinetic energy that this system have is like and then the normal or the usual kinetic energy equation that we usually know, because this thing is not rotating, the mass is not rotating, it's just moving alongside like our x direction that we are considering, is just moving like this part right here, doesn't have any circular motion with an axis, this mass. So um since this mass just have like a regular velocity, for saying some kind of sense, regular velocity. So the only kinetic energy that the system have is 1/2 of mv squared. Okay, and I will be rewriting this like mx dot square, because I'm mentioning it will just be moving alongside the x direction considered. Okay, so we'll be using the equations that we considered before for changing to polar coordinates. It will be easier also to work these problems in polar coordinates. So changing this part right here, 1/2 of m l theta dot square, it will be 1/2 m l square theta dot square. So this is the kinetic energy of our system. And the potential energy. Potential energy is a little bit more interesting. It's not hard to consider, but um, we need to do a little consideration right here. Okay, so the only potential energy that we have is related with the height that this mass m will be increasing or decreasing their height with some point of reference. Okay, and since this um, is not moving like a spring, so we do not have any potential energy related to a spring. So the only potential energy that we have, that we will be having right here, is mgh. The interesting part right here is what exactly value have this h. So I will be doing here, this is the system in a rest position, the same as m, and this will be the h, this here, this part, this is our h. Okay, so how we find this value? So if you notice, all of this will have a value on of L, the length of the rope. Okay, and we need to subtract that distance of this part right here, and this is very easy, because if you see this part is a, a triangle, and we can find this part using trigonometric relations. You know, like the cosine of theta will be this. I will call x. No, we already use x, so I will say um, w. Just say one variable. W over L. So W will be L cosine theta. Okay, perfect. So this is our um, this part right here. So our height would be L minus W, and this will be equal to L minus L cosine theta. This will be equal to L1 minus cosine theta. Okay, perfect. So this our expression for the potential energy will be mg L1 minus cosine of theta. Okay, perfect. So we already have all of our the parts that we can use for our Lagrangians. Or Lagrangian will be something like 1/2 of m L squared theta dot square minus mg L1 minus cosine of theta. Okay, so this is our Lagrangian. So first we'll be considering the partial derivative with respect of the velocity. So the partial L with respect of the velocity, the only coordinate that we are considering, because if we consider Cartesian coordinates, we need to consider the two different derivatives, the derivative with respect of x and the derivative with respect of y. So we change that the coordinates from Cartesian coordinates to polar coordinates to make it easier. So we can just consider one coordinate that will be the angular here. So we have here just to consider the position with respect to the angle, and we have the only velocities, the angular velocity here. So our derivative will be m L squared theta dot, and since we don't have any expression for the velocity here, will be 0. Okay, and this will be our first part. And now, based on the Lagrangian equations, now we need to do the derivative of this expression with respect of the time. So the dt of dl d theta with the dt m l square theta dot. The only thing that is changing is the velocity. The only two things right here are constant, so it will be m l square theta double dot. Okay, so this is our first part of our equation, and the second part will be uh, using the derivative with respect of the position. Okay, so again, the only position that we need to consider is the angular position, since the other things are constant. Okay, so we have right here, this is our Lagrangian. This expression doesn't have any position related, so this will be 0 minus mgl 1 plus sine, no, this is 0, sorry, it will be mgl plus sine theta, so minus mgl sine theta. Okay, so this is basically all the parts that we need for Lagrangian. So basically we will be having m l squared double dot minus this thing right here, minus mg l sine theta equals to 0. Okay, and we can be reducing this thing, and we have m, also the m's, and then the m's can be removed from the equation. We have l double dot plus g sine theta equals to 0, and leaving the acceleration alone, we will have theta double dot g l sine theta equals to 0. And there you have it. Basically, this is the same equation that we have right here. So as you can see, it's very interesting because with two different approaches we have the same results, and this is one of the incredible things here in physics, because two different things, one we are considering forces, the Newtonian mechanics considering forces, the Lagrangian mechanics are considering the energy, relating the potential energy and the kinetic energy of a system with the Lagrangian, and with both of those approaches we got the same result. So I found that very interesting. I hope that you found too interesting, and that will be all for today. Thank you for joining, and hope you have a nice rest.